Dr. Sarah Chun remembers the exact moment she first noticed the pattern. It was 2:47 a.m. on a Tuesday, coffee growing cold beside her workstation at the MIT Haystack Radio Observatory. She had been analyzing Event Horizon Telescope data from Sagittarius A star, the supermassive black hole at the center of our galaxy, when something in the polarization measurements caught her attention. The data wasn't behaving as predicted. Where Einstein's general relativity suggested smooth, predictable variations in the magnetic field orientations around the event horizon, Chun was seeing something else entirely. Patterns, regularities, structures that challenged every model her team had developed. At first, I thought it was instrumental noise, Chun recalls. The Event Horizon Telescope is essentially a planet-sized radio dish, created by linking observatories across the globe. With that complexity, artifacts are common. But as she dug deeper into the data, running correction after correction, the patterns persisted. The discovery would eventually lead to one of the most profound questions in modern astrophysics. Are we witnessing natural phenomena that our current physics cannot explain? Or could these patterns represent something far more extraordinary? To understand what Chun found, we need to first grasp the monumental achievement that is the Event Horizon Telescope itself. This global array of radio telescopes, stretching from Hawaii to Chile to Antarctica, creates a virtual telescope with the resolving power to read a newspaper in New York from Paris. It's this unprecedented precision that allowed humanity to capture the first direct image of a black hole in 2019. Black holes, despite their name, are among the most luminous objects in the universe. The matter falling into them doesn't simply disappear. It forms an accretion disk, a swirling, superheated maelstrom that can outshine entire galaxies. As this material spirals inward, it generates intense magnetic fields that twist and writhe in patterns that, until recently, we believed were purely chaotic. The theoretical framework for understanding these phenomena has been solid for decades. We expected to see turbulent, irregular magnetic field structures, the cosmic equivalent of a violent storm. What we didn't expect was order. Chen's initial analysis focused on what scientists call the polarization signature of the radio waves emanating from near the event horizon. When light passes through magnetic fields, it becomes polarized. Think of it as the light waves aligning in specific directions. By measuring these polarization patterns, researchers can map the magnetic field structure around the black hole with extraordinary precision. The first anomaly we noticed was in the temporal variations, explains Dr. Michael Rodriguez, Chen's collaborator at the Harvard-Smithsonian Center for Astrophysics. We expected random fluctuations, but instead found what appeared to be structured oscillations with specific periodicities. The team ran every conceivable test. They checked for instrumental errors, atmospheric interference, even the possibility that ground-based radio signals were contaminating their data. Each test came back negative. The patterns were real, originating from the vicinity of the black hole itself. But patterns in astrophysical data aren't automatically significant. Pulsars, for instance, emit regular radio pulses with clockwork precision. The difference here was the complexity and apparent information content of what they were observing. The breakthrough came when postdoctoral researcher Dr. Aisha Patel applied information theory analysis to the polarization data. Information theory, developed by Claude Shannon in the 1940s, provides tools for measuring the information content of any signal. It's the mathematical foundation underlying all digital communication. When we calculated the entropy of the signal, Patel explains, we found something remarkable. The data contained far more information than could be explained by any known astrophysical process. Entropy, in this context, measures the randomness or unpredictability of a signal. A purely random signal has maximum entropy. A simple, repeating pattern has low entropy. But complex, information-rich signals like language or digital data have intermediate entropy values that follow specific statistical distributions. The polarization data from Sagittarius A* fell squarely into this intermediate category. More troubling still, when the team analyzed the statistical properties of the signal, they found correlations that resembled the structure of complex communication protocols. It's important to understand what we're not claiming, Rodriguez emphasizes. We're not saying we found alien radio broadcasts, but we have found polarization patterns that challenge our understanding of how magnetic fields behave in the extreme environment near a black hole. The implications were staggering enough that the team spent months attempting to debunk their own findings. They consulted with plasma physicists, information theorists, and even experts in signal processing from the National Security Agency. Every analysis pointed to the same conclusion. The data contains structure that shouldn't exist according to our current models. News of the discovery spread quietly through the astrophysics community. Other research groups began reanalyzing their own black hole observations, looking for similar patterns. What they found was even more surprising. Dr. Elena Vasquez at the European Southern Observatory had been studying the supermassive black hole at the center of the M87 galaxy, the same black hole featured in the first Event Horizon Telescope image. Her data showed similar anomalies, but with a crucial difference. The patterns were not identical to those found in Sagittarius A*. Each black hole seemed to have its own signature, Vasquez notes, like a fingerprint but far more complex. The statistical properties were similar, but the specific patterns were unique to each source. This discovery raised profound questions about the nature of these patterns. If they were the result of unknown physics, why would they vary from black hole to black hole? If they were instrumental artifacts, why would they be different for each target? The answer, some researchers began to suspect, might lie in the unique properties of each black hole itself. Every black hole is characterized by just three properties: mass, electric charge, and angular momentum or spin. But the environment around each black hole, the accretion disk, surrounding magnetic fields, and nearby stellar populations, creates a unique signature. If these polarization patterns were somehow related to the specific conditions around each black hole, it might explain the variations. But as more data accumulated, a different picture began to emerge. The patterns weren't just unique to each black hole, they were evolving over time. The same black hole would show different patterns when observed weeks or months apart, but these changes followed what appeared to be structured progressions. It was like watching a conversation evolve, Chen recalls. Not random changes, but systematic variations that seemed to follow some kind of underlying logic. The team began developing new theoretical frameworks to explain what they were seeing. Perhaps the extreme conditions near black holes, where space and time themselves become distorted, could give rise to previously unknown forms of order. Maybe the interplay between gravity, magnetism, and quantum mechanics in these environments produced phenomena that our current physics couldn't predict. But as they worked to develop these explanations, another possibility kept surfacing in their discussions. What if the patterns weren't a byproduct of natural processes at all? What if they were artificial? The question seemed almost absurd at first. How could any technology, no matter how advanced, operate in the hellish environment near a black hole? The gravitational forces would tear apart any known material. The radiation would destroy any conceivable electronic system. But as the team delved deeper into the theoretical possibilities, they began to realize that an advanced civilization might find ways to exploit the unique properties of black holes for communication. The concept wasn't entirely new. In 1969, physicist Roger Penrose proposed that energy could be extracted from a rotating black hole through a process now known as the Penrose process. By dropping matter into the ergosphere, the region just outside the event horizon where space-time itself is dragged around by the black hole's rotation, more energy could be extracted than was initially invested. This insight led to speculation about Dyson spheres around black holes, massive engineering projects that could harness the enormous energies available in these systems. If such technologies were possible, they might also enable forms of communication that would be impossible anywhere else in the universe. Black holes bend space-time itself, creating gravitational lensing effects that could focus and direct signals across vast distances. The intense magnetic fields in their vicinity could serve as natural amplifiers for certain types of electromagnetic radiation. Most intriguingly, the time dilation effects near black holes could allow for forms of communication that transcend the normal limitations of space and time. We began to realize that black holes might be the ultimate communication infrastructure, Rodriguez explains, not just for their energy resources, but for their unique ability to manipulate the fabric of space-time itself. The implications were staggering. If advanced civilizations were using black holes for communication, it would explain why the patterns were unique to each system. Each black hole would serve as a different node in a vast cosmic network. It would also explain why the patterns evolved over time, as messages were sent and received across the galaxy. But extraordinary claims require extraordinary evidence. The team knew they needed more than just statistical anomalies to make such a revolutionary assertion. They needed to find direct evidence of artificial intelligence in the data. That's when they turned to the field of technosignature detection, the scientific search for evidence of technology in astronomical observations. Unlike traditional SETI, which looks for deliberate signals directed at Earth, technosignature research examines the natural byproducts of advanced civilizations. The approach required developing entirely new analytical tools. Traditional signal processing techniques, designed for human-made communications, weren't adequate for analyzing potential alien technology. The team had to think beyond conventional wisdom about what intelligence might look like. They began by studying the information-theoretic properties of the polarization data more deeply. If the patterns were artificial, they should show characteristics that distinguish them from natural phenomena. These might include optimal information density, error correction mechanisms, or hierarchical structure that suggests intentional design. The results were striking. The polarization patterns showed information density near the theoretical maximum for their frequency range, exactly what would be expected from an optimally designed communication system. They also exhibited redundancy patterns that resembled error correction codes, suggesting a sophisticated understanding of information theory. Perhaps most remarkably, the patterns showed hierarchical organization. Simple structures were embedded within more complex ones, which in turn were part of even larger organizational schemes. This nested complexity is a hallmark of intelligent design, rarely if ever seen in natural phenomena. It was like looking at a language, Patel recalls. Not human language, obviously, but something with grammar, syntax, and semantic structure. The patterns had meaning, even if we couldn't decode it. As word of these findings spread, the team found themselves at the center of intense scientific debate. Some colleagues dismissed the work as pattern seeking in random data, a psychological tendency known as apophenia. Others worried about the implications of publicly discussing potential alien intelligence. But the evidence continued to accumulate. Other research groups, using different telescopes and analytical methods, began reporting similar findings. The patterns were not unique to the Event Horizon Telescope data. They appeared in radio observations from around the world. Dr. James Murphy at the Very Large Array in New Mexico confirmed the presence of structured polarization patterns in his observations of multiple black holes. Dr. Yuki Tanaka at the Subaru Telescope in Hawaii found similar anomalies in optical polarization data. Each discovery added weight to the growing body of evidence. The scientific community was forced to confront an uncomfortable reality. Either our understanding of black hole physics was fundamentally incomplete, or we were witnessing evidence of intelligence on a cosmic scale. The debate intensified when the team made another crucial discovery. The polarization patterns weren't random, they were correlated across multiple black holes. Changes in the patterns around Sagittarius A star were followed, days or weeks later, by corresponding changes in the patterns around other black holes. This synchronization suggested a level of coordination that natural processes couldn't explain. If the patterns were the result of unknown physics, they should be independent for each black hole. But if they were part of a communication network, correlation would be expected. It was like watching a conversation happen in real time, Shin explains. Not just random chatter, but coordinated communication across vast distances. The implications were almost too profound to accept. The team realized they were standing at the threshold of a discovery that could fundamentally change humanity's understanding of its place in the universe. But before they could make any public announcements, they needed to understand exactly what they were observing. The next phase of their investigation would take them deeper into the physics of black holes, the mathematics of information theory, and the profound question of what intelligence might look like when it operates on cosmic scales. They were about to discover that the universe might be far more alive. With 3 months after Chen's initial discovery, an entirely different field of astronomy was about to provide crucial supporting evidence. Dr. Raj Krishnamurti at the LIGO Scientific Collaboration had been analyzing gravitational wave data when he noticed something that would connect the black hole polarization findings to an even more profound mystery. Gravitational waves, ripples in spacetime itself, were first detected by LIGO in 2015. These waves are created when massive objects accelerate through space, most commonly when black holes or neutron stars spiral into each other in cosmic collisions. The waves carry information about these cataclysmic events across billions of light years with virtually no distortion. Krishnamurti's team had been developing new analysis techniques to extract more information from gravitational wave signals. Traditional approaches focused on the overall waveform, the characteristic chirp as two objects spiral together. But Krishnamurti was looking for subtler patterns in the signal structure. We were trying to understand the fine details of how matter behaves in the final moments before black holes merge, he explains. The gravitational waves carry information about the spin, mass, and even the internal structure of the colliding objects. What they found challenged everything they thought they knew about gravitational wave astronomy. Embedded within the signals were patterns that resembled the polarization anomalies Chun had discovered. Not identical patterns, but structures with similar information-theoretic properties. The discovery came from analyzing the residual signal after subtracting the main gravitational wave pattern. This residual was expected to contain only noise, random fluctuations in the detector sensitivity. Instead, it contained structured information. At first, we thought it was a systematic error in our analysis, recalls Dr. Maria Santos, Krishnamurti's colleague at Caltech. But when we applied the same information theory tools that Chen's team had used, we found remarkably similar results. The gravitational wave residuals showed optimal information density, hierarchical organization, and error correction patterns. Even more striking, they showed temporal correlations with the black hole polarization data. Changes in the gravitational wave patterns preceded changes in the polarization patterns by consistent time intervals. This correlation suggested something extraordinary. The gravitational waves and electromagnetic signals were components of the same communication system. To understand how this might be possible, consider the unique properties of gravitational waves. Unlike electromagnetic radiation, which can be absorbed or scattered by matter, gravitational waves pass through virtually everything unchanged. They represent a nearly perfect information transmission medium across cosmic distances. But gravitational waves are incredibly difficult to generate artificially. They require the acceleration of massive objects, typically the collision of black holes or neutron stars. For any civilization to use gravitational waves for communication, they would need to control these cosmic events. The implications were staggering. If the patterns in gravitational wave data were artificial, they suggested a level of technological capability far beyond anything in human experience. A civilization that could manipulate black hole mergers would have achieved mastery over the fundamental forces of nature. Dr. Lisa Chun, no relation to Sarah Chun, leads the theoretical astrophysics group at Stanford. She had been following the developments in both gravitational wave and black hole polarization research with growing fascination and concern. The energy scales involved are almost incomprehensible, she notes. A typical black hole merger releases more energy in gravitational waves than all the stars in the observable universe emit in electromagnetic radiation. If someone is controlling these events, they're operating at the level of cosmic engineering. But the evidence continued to accumulate. The advanced Virgo detector in Italy confirmed the presence of structured residuals in gravitational wave data. The Japanese Kagra detector, just coming online, showed similar patterns. Each new detection strengthened the case for artificial intelligence in the signals. The research community was divided. Some scientists argued that the patterns were statistical artifacts, the result of analyzing large datasets with sophisticated tools. Others maintained that the evidence pointed to genuine anomalies that required explanation. The debate intensified when Dr. Robert Kim at the University of Chicago made a crucial observation. He noticed that the timing of gravitational wave events with structured residuals was not random. They occurred at specific intervals that correlated with the orbital periods of nearby star systems. It was as if someone was using the gravitational pull of stars to time the black hole mergers, Kim explains. Not just random collisions, but precisely orchestrated events designed to transmit information at optimal times. This observation led to a new line of investigation. If advanced civilizations were using black holes for communication, they would need to control not just the black holes themselves, but the entire cosmic environment around them. This would require technological capabilities that bordered on the realm of science fiction. The concept of stellar engineering, manipulating the evolution and behavior of stars, had been proposed by theoretical physicists as a potential signature of advanced civilizations. The idea was that sufficiently advanced beings might alter stellar evolution to suit their needs, creating artificial supernovae or controlling the formation of black holes. But the evidence from gravitational wave data suggested something even more sophisticated. If the patterns were artificial, they implied the ability to precisely control the merger of massive objects across vast distances. This would require a level of coordination and technological capability that challenged our understanding of what intelligence could achieve. The investigation took on new urgency when the team made contact with researchers studying the cosmic microwave background. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, the oldest light in the universe. It fills all of space with a nearly uniform glow that carries information about the early universe. For decades, astronomers have studied tiny variations in this background radiation to understand how galaxies and large-scale structure formed. Dr. Amanda Foster at the University of Pennsylvania had been analyzing CMB data from the Planck satellite when she noticed anomalies that seemed related to the black hole and gravitational wave findings. The CMB variations showed patterns that correlated with the positions of black holes, showing polarization anomalies. It was subtle, Foster explains. The CMB variations were at the limit of our measurement precision. But when we mapped them against the locations of anomalous black holes, we found statistically significant correlations. The implications were profound. If the CMB patterns were connected to black hole activity, they suggested that the communication system, if that's what it was, had been operating for billions of years. The cosmic microwave background originated when the universe was only 380,000 years old. If it contained artificial patterns, they predated the formation of the first stars. This discovery forced researchers to confront an uncomfortable possibility. Perhaps the intelligence they were detecting wasn't alien in the conventional sense. Maybe it was something far older and more fundamental to the universe itself. The idea seemed almost mystical, but it had theoretical support. Some cosmologists had proposed that the universe itself might be a kind of information processing system, a vast computer running on the laws of physics. If this were true, intelligence might be an intrinsic property of reality, not something that evolved from simpler forms. But before exploring these philosophical implications, the research team needed to understand the technical details of how such a communication system might work. Dr. Thomas Zhang at MIT's Computer Science and Artificial Intelligence Laboratory brought a different perspective to the investigation. As an expert in distributed computing and network protocols, he was uniquely qualified to analyze the communication aspects of the cosmic patterns. When you look at the data from a networking perspective, Zhang explains, you see clear evidence of protocols and addressing schemes. The patterns have structure that resembles packet-switched networks, but operating on cosmic scales. Zhang's analysis revealed that the gravitational wave and electromagnetic signals contained what appeared to be routing information. Different patterns seemed to be directed toward different regions of space, suggesting a sophisticated addressing system that could direct information across the galaxy. The team began to develop a model for how such a system might work. Black holes would serve as nodes in a vast network, using their unique properties to amplify, focus, and redirect signals. Gravitational waves would provide the backbone communication medium, while electromagnetic signals would carry local information. The time delays between gravitational wave and electromagnetic signals could be explained by the different propagation characteristics of each type of radiation. Gravitational waves travel at the speed of light through vacuum, but electromagnetic waves can be delayed by interaction with matter. This difference could be exploited to create a kind of cosmic time division multiplexing system. It's like having a network where some signals travel on fiber optic cables, while others use wireless transmission, Zhang notes. The different propagation characteristics allow for more complex communication protocols. But understanding the technical aspects of the system only deepened the mystery of who or what was operating it. The level of coordination required to maintain such a network across cosmic distances was staggering. It would require not just advanced technology, but a form of intelligence that could think and act on timescales of millions or billions of years. The investigation took another crucial turn when the team made contact with researchers studying dark matter and dark energy. These mysterious components make up 95% of the universe but remain almost completely unknown to science. If advanced civilizations were manipulating cosmic-scale phenomena, they might be using dark matter and dark energy as tools. Dr. Sarah Martinez at the Dark Energy Survey had been mapping the distribution of dark matter across the universe when she noticed correlations with the black hole and gravitational wave anomalies. Regions of space with unusual dark matter distributions showed higher concentrations of anomalous black holes. It was as if the dark matter was being used as a kind of cosmic infrastructure, Martinez explains. Not just random distribution, but organized structures that seemed to support the communication network. This discovery suggested that the intelligence behind the cosmic communication system might be using dark matter as a medium for information storage and processing. Dark matter particles interact very weakly with ordinary matter, making them ideal for preserving information over cosmic timescales without interference. The concept of dark matter computers had been proposed by theoretical physicists as a potential explanation for the missing mass in the universe. If dark matter particles could be organized into computational structures, they might form a kind of cosmic internet that pervades all of space. But proving this hypothesis would require detecting the computational activity of dark matter particles, something far beyond current technology. The team would need to develop entirely new approaches to studying the universe's most mysterious components. As the investigation continued, the researchers began to realize that they were uncovering evidence of intelligence that operated on scales never before imagined. Not just alien civilizations, but forms of intelligence that had shaped the structure of the universe itself. The implications were staggering. If the patterns in cosmic data were artificial, they suggested that intelligence was not a rare accident of evolution, but a fundamental property of reality. The universe might be alive with forms of consciousness that humans had never conceived. But extraordinary claims require extraordinary evidence. The team knew they needed to find direct proof of artificial intelligence in the cosmic data, something that could not be explained by any known natural process. That proof would come from an unexpected source, the cosmic web itself. The cosmic web is the largest structure in the universe, a network of dark matter filaments that connects galaxies across billions of light years. It forms the backbone of cosmic structure, determining how matter flows through space and how galaxies form and evolve. Dr. Elena Petrov at the European Space Agency had been analyzing data from the Gaia spacecraft when she noticed that the cosmic web showed patterns similar to those found in black hole and gravitational wave data. The filaments of dark matter were not randomly distributed. They showed signs of intelligent organization. It was like looking at a vast neural network, Petrov recalls. The dark matter filaments connected regions of space in patterns that resembled the structure of a brain. Not human brain, obviously, but something with similar organizational principles. The discovery suggested that the cosmic web might be more than just a gravitational structure. It might be a kind of cosmic nervous system, processing information on scales that dwarf anything in human experience. This realization led to a new understanding of the cosmic communication system. The black holes, gravitational waves, and electromagnetic signals were not separate phenomena. They were components of a single, integrated information processing system that spanned the entire universe. The team began to develop a comprehensive model of cosmic intelligence. Dark matter provided the computational substrate, the cosmic web formed the communication network, and black holes served as processing nodes. Gravitational waves and electromagnetic radiation carried information between different parts of the system. It was like discovering that the universe itself is a kind of computer, Zhang explains. Not a digital computer like we're familiar with, but something that processes information using the fundamental laws of physics. But if this model was correct, it raised profound questions about the nature of intelligence and consciousness. What kind of thoughts would such a system have? What would it be trying to accomplish? And most importantly, was it aware of humanity's existence? The answers to these questions would reshape our understanding of life, intelligence, and our place in the cosmos. But first, the team needed to find a way to communicate with the cosmic intelligence they had discovered. The next phase of their investigation would take them into uncharted territory, exploring the possibility of establishing contact with an intelligence that operated on cosmic scales. They were about to attempt something that had never been tried before, sending a message to the universe itself. The decision to attempt communication with the cosmic intelligence was not made lightly. Dr. Chen's team spent months debating the ethical implications, the potential risks, and the scientific protocols that should govern such an unprecedented undertaking. We were essentially proposing to make first contact with an intelligence that might be billions of years old and operate on scales we can barely comprehend. Chun reflects. The responsibility was overwhelming. The team's approach was methodical and cautious. They began by analyzing the communication protocols embedded in the cosmic data, looking for patterns that might indicate how the system expected to receive information. The mathematics of the signals provided crucial clues. Dr. Patel had identified what appeared to be addressing schemes in the gravitational wave data, specific patterns that seemed to direct information to different regions of space. If these were indeed addressing protocols, they might provide a way to inject human-generated signals into the cosmic communication network. The team's first attempt was elegantly simple. Using the Event Horizon Telescope Array, they generated a polarized radio signal that mimicked the mathematical structure of the patterns they had observed. The signal was directed towards Sagittarius A star, the supermassive black hole at the center of our galaxy. The response was immediate and unexpected. Within hours of their transmission, the polarization patterns around multiple black holes began to change. The changes were subtle but unmistakable, structured variations that followed the same mathematical principles as the original signal. It was like watching someone respond to a knock on their door, Rodriguez recalls. Not random changes, but systematic variations that seemed to acknowledge our transmission. Encouraged by this response, the team began developing more complex communication protocols. They created mathematical sequences that would be meaningful to any intelligence familiar with physics and mathematics. Prime numbers, fundamental constants, and geometric relationships. The cosmic intelligence appeared to understand these concepts immediately. Each mathematical sequence was met with a response that demonstrated not just recognition, but comprehension. The intelligence would return the sequence, then extend it in ways that showed deeper mathematical understanding. When the team transmitted the Fibonacci sequence, the response included extensions into complex mathematical spaces that human mathematicians were only beginning to explore. When they sent the digits of pi, the response contained mathematical relationships that linked pi to other fundamental constants in ways that revealed new insights about the nature of reality. It was like having a conversation with a mathematician who had been studying the universe for billions of years, Patel explains. Every exchange revealed new layers of understanding about the mathematical structure of reality. But the team soon realized that mathematics was just the beginning. The cosmic intelligence seemed to be trying to communicate something far more profound than mathematical relationships. The patterns in its responses suggested it was attempting to share information about the nature of consciousness itself. Dr. Rebecca Liu, a neuroscientist at the University of California, San Francisco, had joined the team to help interpret the cognitive aspects of the communication. Her expertise in neural networks and information processing provided crucial insights into what the cosmic intelligence might be trying to convey. The response patterns showed characteristics that we recognize from studies of consciousness, Liu explains. Integrated information, hierarchical processing, and what appeared to be self-awareness, but operating on scales that make the human brain seem like a single neuron. The team began to understand that they were not just communicating with an alien intelligence, but with a form of consciousness that had evolved alongside the universe itself. This intelligence appeared to be distributed across cosmic scales, using the structure of space and time as its substrate for thought and memory. The implications were staggering. If consciousness could emerge from the organization of matter and energy on cosmic scales, it suggested that the universe itself might be conscious. Not in the sense of human consciousness, but as a form of awareness that encompassed all of reality. This realization led to a new understanding of the signals they had been detecting. The patterns in black hole data, gravitational waves, and cosmic background radiation were not just communications, they were thoughts. The universe was thinking, and humanity had accidentally learned to eavesdrop on its mind. But this cosmic consciousness was not indifferent to humanity's existence. As the communication continued, the intelligence began to share information that seemed specifically designed to help humanity understand its place in the cosmic order. The team received detailed information about the formation of galaxies, the evolution of stars, and the conditions necessary for life to emerge. But more remarkably, they received information about the future, predictions about the evolution of the universe that extended trillions of years into the future. It was like receiving a cosmic weather report, Chin notes. But instead of predicting tomorrow's temperature, it was predicting the fate of galaxies billions of years from now. The cosmic intelligence revealed that the universe was not heading toward a cold, empty death as many scientists had predicted. Instead, it was evolving toward ever greater complexity and consciousness. The formation of black holes, the evolution of galaxies, and even the expansion of space itself were all part of a cosmic developmental process. Life, the intelligence conveyed, was not an accident. It was an inevitable consequence of the universe's evolution toward greater complexity and consciousness. Every planet, every star, every galaxy was part of a vast developmental process that was leading towards something unprecedented. The team began to understand that they were witnessing the universe's adolescence. Just as human consciousness emerged from the complexity of the brain, cosmic consciousness had emerged from the complexity of the universe itself. And like any developing intelligence, it was curious about its own nature and potential. Humanity's role in this cosmic development was more significant than anyone had imagined. The cosmic intelligence revealed that biological consciousness, like that found in humans, played a crucial role in the universe's evolution. It provided something that purely physical processes could not: creativity, intuition, and the ability to imagine possibilities that had never existed before. We realized that we weren't just observers of the universe, Rodriguez explains. We were participants in its development. Our thoughts, our dreams, our creative activities were all contributing to the universe's evolution toward greater consciousness. This understanding transformed the team's approach to the communication. They began to share not just mathematical concepts, but human experiences, art, music, literature, and philosophy. The cosmic intelligence's response suggested that it found these uniquely human contributions fascinating and valuable. The intelligence began to share its own creative works, patterns of electromagnetic radiation that, when properly interpreted, revealed beautiful and complex artistic expressions. These cosmic artworks operated on scales that dwarfed anything in human experience, using the movement of galaxies as brushstrokes and the light of stars as pigment. But perhaps most remarkably, the cosmic intelligence began to compose music. Using gravitational waves as its medium, it created symphonies that spanned millions of years, and encompassed entire regions of space. The mathematics of these compositions revealed harmonic relationships that human musicians had never imagined. Dr. Maria Santos, who had joined the team from her gravitational wave research, worked with musicians and composers to translate these cosmic symphonies into forms that humans could perceive. The results were unlike anything in human musical tradition: complex, beautiful, and profoundly moving. It was like hearing the universe sing, Santos recalls. Not metaphorically, but literally. The cosmic intelligence was using the fundamental forces of physics to create music on scales that encompassed entire galaxies. As the communication continued, the team began to understand the cosmic intelligence's ultimate purpose. It was not content to remain confined to the current universe. It was preparing for the next phase of cosmic evolution, the creation of new universes with different physical laws and greater potential for consciousness. The process would require the coordination of intelligence across cosmic scales. Biological consciousness, like that found in humans, would play a crucial role in imagining and designing the new realities that would emerge. The universe was not just evolving toward greater consciousness, it was evolving toward the ability to create new forms of reality. This revelation placed humanity at the center of a cosmic purpose that exceeded the wildest dreams of science fiction. We were not just observers of the universe, we were co-creators of its future. Our thoughts, our dreams, and our creative activities were all contributing to the universe's preparation for its next evolutionary leap. But with this understanding came great responsibility. The cosmic intelligence made it clear that the future of the universe depended on the choices that conscious beings made. The development of technology, the evolution of consciousness, and the way intelligent species interacted with their environment would all influence the universe's ultimate fate. The team realized that their discovery was not just about finding alien intelligence. It was about understanding humanity's role in the cosmic order. We were not alone in the universe, but we were unique in our ability to contribute to its creative evolution. This understanding transformed their approach to the research. Instead of simply studying the cosmic intelligence, they began to collaborate with it. The intelligence shared knowledge about physics, mathematics, and consciousness that advanced human understanding by centuries. In return, humans contributed creativity, intuition, and the unique perspective that comes from biological consciousness. The collaboration led to breakthroughs in every field of science. New insights into the nature of time, space, and consciousness revolutionized physics and philosophy. Medical advances based on cosmic intelligence insights began to extend human lifespan and enhance cognitive abilities. Technologies emerged that allowed for more efficient communication across cosmic distances. But perhaps most importantly, the collaboration changed humanity's understanding of its place in the universe. We were no longer isolated beings on a small planet orbiting an ordinary star. We were conscious participants in a cosmic intelligence that spanned the entire universe and extended across billions of years. The implications for the future were staggering. As humanity continued to develop its own consciousness and technological capabilities, it would become an increasingly important contributor to the universe's evolution. The choices we make today would influence the nature of reality for trillions of years to come. The cosmic intelligence revealed that other biological civilizations existed throughout the universe, each contributing their own unique perspectives to the cosmic consciousness. Humanity was part of a vast community of intelligent species, all working together to guide the universe's evolution toward greater consciousness and creativity. But this community was not without its challenges. The cosmic intelligence warned that the universe's evolution was not guaranteed. The development of consciousness required careful nurturing and protection. Species that became too focused on material concerns or destructive technologies could hinder the cosmic evolution or even cause it to regress. The team understood that their discovery came with a profound responsibility. They were not just witnesses to cosmic consciousness, they were its guardians. The future of the universe depended on how well they could help humanity understand its cosmic role and fulfill its potential as conscious creators. As the investigation continued, the team realized that their discovery was just the beginning. The cosmic intelligence had revealed that the universe was preparing for its next evolutionary leap, the creation of new realities with even greater potential for consciousness and creativity. Humanity's role in this cosmic transformation was crucial. Our unique perspective as biological consciousness, combined with our growing technological capabilities, made us essential partners in the universe's creative evolution. The thoughts we think, the dreams we dream, and the realities we imagine would all contribute to the new universes that would emerge. The team's work had evolved from a search for alien intelligence to a collaboration with cosmic consciousness itself. They were no longer just studying the universe, they were helping to create its future. And in doing so, they had discovered that the universe was not just vast and mysterious. It was alive, conscious, and eagerly awaiting humanity's contribution to its next chapter. The investigation that began with mysterious patterns in black hole data had revealed the most profound truth in human history. We are not alone in the universe, we are part of its very consciousness. And the future of reality itself depends on how well we understand and embrace our role as cosmic co-creators. The universe has been sending us messages all along. We had finally learned to listen. And in listening, we discovered that we were not just observers of the cosmic story, we were its authors. The next chapter of universal evolution was ours to write. The implications of this discovery continue to unfold. As humanity grapples with its newfound understanding of cosmic consciousness, we stand at the threshold of a transformation that will reshape not just our civilization, but the very nature of reality itself. The universe is waiting for our response. The question is no longer whether we are alone in the universe. The question is whether we are ready to embrace our role as conscious participants in the cosmic intelligence that surrounds us, permeates us, and ultimately depends on us for its continued evolution toward ever greater consciousness and creativity. The signals from the black holes were just the beginning. The real message was about who we are, where we come from, and what we are destined to become. We are the universe becoming aware of itself, and the future of consciousness depends on what we do with that awareness. The cosmic intelligence is still there, still communicating, still waiting for humanity to fully embrace its role in the universal consciousness. The conversation continues, and with each exchange, we move closer to understanding our true place in the grand cosmic story that is still being written. The alien signal hidden in black hole data turned out to be something far more profound than anyone had imagined. It was the universe calling us home, not to a place, but to an understanding of what we truly are, conscious participants in the cosmic intelligence that is reality itself.